Okay, good morning, everybody. Welcome to this webinar. My name is Monje from Labyrinth project. I will be responsible of managing the agenda and introducing the different speakers today. I'm going to share the agenda with you. The idea, as you can see here, is to have different presenters from the three main projects we are sharing information today from, right? Which are Rapid, Labyrinth, and Drones for Safety. So we have a tight agenda, 3 hours and around 45 minutes for each project. We will start with Drones for Safety, and for each project we will have a short presentation of each project, and then several speakers, 4 speakers, PhD students, summarizing the main contributions, their main contributions in 5 minutes. So the idea is that finally, after each project presentation, we have 10 minutes for questions and answers, right? So for questions and answers, I encourage you to write your questions using the chat. And then later, the speakers will answer the questions vividly using the microphone, so that this is more active and easy to follow, right? So from Drones for Safety, we have, as the leader presenting the project, we have Emad Malki, and then we will have 4 of the PhD students. They will present each other when starting their presentations. For the Rapid project, as responsible for the project and presenting the main ideas of the project, we have James Riordan. And then for Labyrinth, I will be myself responsible for presenting the overall objectives, and also we will have the 4 PhD students presenting. Finally, the last 10 minutes will be for the webinar closure and for solving any questions you may have. And I must tell you that the session will be recorded with the aim of spreading the knowledge through the different social media and have the information uploaded in the different web pages of each project. So hopefully a wide audience will be able to read and check the information, the knowledge we are sharing here today. Thanks for coming. This is very important for our community. I'm sure you will enjoy the different presentations we have prepared for you all. And please be participative. This is part of the session, and it will be more rich if you participate, asking questions and commenting on the different concepts or ideas that you will be able to see. Okay, so that's all from my side. I will stop sharing my presentation now, and now this is the turn. We are starting with Drones for Safety. So the project overview will be presented by Emad Malki. Welcome, Emad. This is your turn now.
Okay. Thank you so much for the kind introduction and for the excellent organization.
You're welcome.
I will put the work hopefully in full screen now, and let's see if it can. No, a second. Yeah, let's do it like this. So good morning, everyone. My name is Emad Ebeid. I work as an associate professor at the University of Southern Denmark, and I'm the project coordinator of Drones for Safety project. So the project has an aim to develop an autonomous drone system to inspect transport infrastructures, and the drones has to do that autonomously and to recharge from the nearby energy sources like overhead power lines, and also to fly in a swarm, so to do the mission collaboratively. When it comes to our objectives, so we see a need to build energy harvesters for drones, so they have to be lightweight so the drone can carry them. We have to do also efficient inspection, so how the drone can detect defects autonomously, and how they can collaborate and exchange data. and also if something went wrong, how we can like release or safely fail or leave the area of inspection without endangering it, and do that all autonomous. When we look to the past or today, how they do inspection, you can see here there is a forklift with a person looking underneath the bridge to do this like manual inspection, or they physically calculate the distance between the rails to be sure that they are aligned and in parallel. And they have also machine, and they do that mainly every day to assure that the transport infrastructure are safe. Well, so we are trying to change this scene to do it more advanced, and here we come with a special technology in which the drones can replace the human. So here we fly drones to inspect bridges. When their battery goes low, they go to the nearby power line to recharge, and then they fly back. So you can see that drones are commuting between the bridge and the power lines to recharge. Similar scenario can be applied to railways. The drone can recharge from the overhead railway cables, staying outside the rail track, and inspect the rails and then the top part of the cables here. These drones are operating under a cloud service, sending to them the mission and also receiving the data from the drones and present it to the end users. Maybe one will ask, but do we really have nearby infrastructures like this? So when we make our calculation, we could see around 70% of bridges in Europe are within 3 kilometer distance of power lines. So that is quite okay to fly and inspect and so on. Yeah, and here we have in this little table also showing the case in Italy, like also even higher numbers of bridges are near power line cables. Yeah, so a futuristic scenario, the drone will be landed on the power lines, recharge, and then fly, taking pictures, analyze, and sending, if there is something wrong they detect, sending them to the cloud, and then they do the same with railway cables. So we see the system consists of a set of drones. They can self-recharge. So here we speak about like a drone can do that without modifying the infrastructure, which is a new thing in the project. So how to do that autonomously, land on the power line and recharge, and at the same time running onboard AI algorithms to filter the pictures and send the relevant one to the end user. The project has 4 technical work packages, and we are in the middle of that. One related to energy harvesting, and here we use inductive coupling to harvest from AC lines and other techniques for DC lines, and also work with AI for fault detection and 3D modeling, and drone design and the collaborative system, and the mission control and navigation. The expected impact of the project is to have a safe and secure increase of overall civil transport system, and also for the cargo and personal mobility, and that also will have a reflection to the economical growth and also an integration with the use space. And we see that also like quite well in the same direction of the United Nations Sustainable Development Goals, to have sustainable cities, to have a secure transport infrastructure, and of course that comes towards using drones that contribute to the global climate target to lower CO2 instead of using vehicles or helicopters. The project has 9 partners from 5 EU countries. They work together in order to achieve that. So 3 universities and research institute, and companies and end users for presenting the project to the market. If you have any questions, you can write to me an email, or you can check our group website. Thank you.
Thank you very much, Emad. A very interesting project. So let's go now with the first speaker from Drones for Safety, which is Frederik, which is already there. Who is already there? Hi, Frederik.
Yes, hello.
Hello. So you have 5 minutes for your presentation. You can start if you want.
Yes. Can you see my presentation?
Perfectly well. Thank you.
Okay, that's good. So hello, everybody. My name is Frederik Nyboe. I'm a PhD fellow at the University of Southern Denmark under the supervision of Emad, from whom you just heard. So I work on the Drones for Safety project, primarily in two different fields. One is perception of power lines, and the other is control, embedded control for directing the drone up to land on the power line. And when I say land on the power line, I mean reaching the power line from below and grasping the power line such that we can recharge from the power line. So this is what I will talk about today. And I've added this very modest initial studies under my title here, because that is essentially what my presentation will be about, the initial considerations in terms of how we're going to actually facilitate this landing on the power line. So a little bit of background. In general, we see now a shift in how drones are operated, especially within transport and infrastructure usage. So where before drones were merely used to take pictures from afar from the object of interest, we now use drones in transport and infrastructure for several purposes. First of all, we need to be able to operate near objects, so we are actually now flying close to infrastructural objects, where as before we tried to keep away from these objects. And also we see some contact operations now happening within this field. One of the examples could be what we're trying to aim, or what we're aiming to do in our team, that is to actually touch the cable and hang on to the cable. And then, of course, there's the field of aerial manipulation. So in general, we have now higher complexity of the tasks that we are trying to do. Also, when we're trying to operate outside, we need to be able to reject wind disturbance. And additionally, we have in general more complex UAV systems and not just simple quadcopters anymore. So we believe in our team that the grasping of power line cables is a good case study for some of these challenges. And I think the technology that we develop here is generically applicable to other cases within the field of transport and infrastructure for drones as well. And we see here an image from some of the results from our team, which my colleague, can you please mute your microphones?
Yes, please. So Pablo, please switch off your microphone. Thank you.
Okay, thanks. Yeah, so some of my colleagues, they have developed this nice system using two LiDARs where they can reach the cable in a simplified manner here. So some of the challenges here in general, when we want to generalize to more complex scenarios, such as when we have wind and when we want to be able to generically attach onto the power cable, some of the objectives that we should consider here is that typically when we have multirotors in standard configurations, they're under-actuated. So we can control X, Y, and Z, and we can control the yaw in general. And we want to latch onto this power line. And one of the things that we need to consider is that the power line cannot be assumed to be parallel to the ground because we have sag in the power line. So first of all, we want to reach a position on the power line. So that will be your first X, Y, and Z in terms of controllability here. Then we want also to align with the power line cable. So we want to align the yaw such that the drone gripper is aligned with the direction of the cable. And additionally, we want to account for the sag in the cable. So if the cable is not perfectly parallel to the ground, then we need, when we reach the point of the cable where we are to grasp, we need the roll of the drone to be aligned also with the cable. And additionally, we want to be able to control the velocity of the drone as well. So when we reach the cable, we want to slow down the velocity as we approach the cable, such that we don't hit the cable with too high velocity. And then, of course, we throw in some wind disturbance in the mix. So we have this multi-objective problem here, which calls for more advanced methods within control than we have previously seen. And we propose to use a version of nonlinear MPC. And nonlinear MPC has seen some very good theoretical results in the previous years, but today we cannot talk about nonlinear MPC without also talking about implementation. So one of the problems with nonlinear MPC, although a very good theoretical control method is that it's very heavy computationally speaking. And this is why we want to use FPGAs to accelerate some of these computations. So we want to use hardware acceleration with FPGAs for enabling onboard implementation of these optimizations, which are underlying the nonlinear MPC algorithm. And this is possible because we have seen in recent years some very highly efficient nonlinear program solvers for FPGAs. And of course, we can do full or partial parallelization of different matrix operations within the FPGA architecture. And then there's whole sorts of things we can do with pipelining and parallel execution using FPGAs. And then, of course, we've seen also some existing proof of concepts for high-speed FPGA-based nonlinear MPC for other purposes than drones. So we want to sort of rethink how we're doing flight computers, and we want to use these Xilinx UltraScale MPSoC chips. So MPSoC is multiprocessing system on chips. So the idea here is that within one chip, you have an APU. This will be a quad-core CPU. You have an RPU, which will be a dual-core CPU optimized for real-time operations. And then you will have this programmable logic, which is the FPGA fabric. So you can customize the digital hardware underlying the CPUs. Our proposed architecture is that we run some sort of high-level operating system on the APU. This could, for example, be Ubuntu running ROS2 middleware in order to facilitate high-level reasoning or high-level flight logic for the system. Then the RPU, which is optimized for real-time purposes, will contain the general flight controller. So that will sort of be the supervisor of the flight controller. And then the programmable logic enables us to accelerate certain parts of the nonlinear MPC algorithm into the FPGA fabric, such that things that are not able to be done sequentially on the CPU, we can do parallelly on the FPGA in order to reach real-time operation, hopefully. So that was my presentation. If you have any questions, you can ask it after my colleagues have presented for the Drones for Safety project, and otherwise you are welcome to drop me an email. Thanks.
Thank you very much, Frederik. Very interesting issue. Of course, I welcome everybody to really ask questions through the chat. And now our next speaker is Nicolaj Haarhoj. Please, Nicolaj, whenever you want, please remember to adjust to the 5 minutes presentation, right? Thank you.
Do you see my presentation?
Yes, perfect.
Okay, good morning. My name is Nicolaj, and I would like to present some of the work that I do for my PhD here at SDU as part of the Drones for Safety program. So the presentation is titled Towards Sufficient Powerline Detection for Autonomous Drone Navigation and Overhead Cable Grasping. And I will outline some of the past work that we have done, some of the current work that we are doing, and some of the future work towards enabling drones to interact with power lines that we are planning to do. In the left image here on this slide, you can see the outdoors test setup that we have here in Odense at the airport close to the university. And the setup consists of 2 pylons connected with 4 cables that we can energize to simulate real-world scenarios when testing our drone setups. The right image shows the kind of data produced by various sensors when looking at this test setup. And so this figure was part of a paper presented at ICOES this year. And in this paper, we surveyed and evaluated various sensor technologies with respect to their usefulness in detecting overhead cable, cables. So in this image, the black pylon and the pink cables are just overlaid, and the actual data, which are the points, is the actual data that we get visualized in with ROS in Arvis. So on this slide, I will go a bit more into depth with the aforementioned ICOES paper. And so on the left here, you can see the drone that we put together for this publication. And here we basically have a test bed with all different kinds of sensors that we were surveying to figure out which were the best for our use case for detecting the overhead power lines. And the kinds of sensors tested were long-range, low-resolution, and short-range, high-resolution solid-state LiDARs, as well as magnetometers, millimeter wave radar, and stereo cameras. All sensors were selected in part based on their relatively low price, the low weight, and power consumption. And I have a short video here showing the data captured in different scenarios from this drone here on the left. Let's play it without sound. Great. So first up are the measurements taken when the drone is stationary on the ground. And here we again see the same data as we saw before. And so these are the 4 sensors in this case that we were interested in. So we have a stereo camera, we have an 8-segment LiDAR, we have a high resolution low range LiDAR, and then we have a millimeter wave radar. And so here we see an RGB image with the produced 3D data from each sensor overlaid on top of the image. So for some of these sensors, we can clearly see the line. And for other of the sensors, we also see a lot of noise, for example, the stereo camera. And so especially what to pay attention to here would be the millimeter wave radar, where we can clearly see that we get pretty good measurements on the lines. Even the furthest line, which is in this case is about 10 meters away, I think. And so next up are measurements during actual flight. And so we just fly around the cables and see what kind of data our sensors produce. In this case, we can see that the stereo camera is again quite noisy. The 8-segment LiDAR is not able to pick up the furthest cables, and the millimeter wave radar is able to pick up all the cables, but only with a very sparse amount of data. Yeah. So here I will shortly talk about the work that we are doing at the moment. And so on the left is the drone, as it were, in the work that we showed previously. And on the right is the drone as it is at the moment. And as you can see, we have significantly reduced the amount of sensors on each drone. And we plan to continue reducing the amount of sensors to achieve a very cheap platform. So essentially what we have on the drone now is few sensors. We have onboard intelligence, which is below this custom-made breakout shield. So we use, as Frederik mentioned before, this heterogeneous platform with an FPGA to accelerate low-level logic, and then an APU to facilitate high-level logic, for example, running Ubuntu and Rust 2. And then we have outfitted the drone with different kinds of custom electronics to facilitate these uses. And so for future work, we are going to enhance the drone platform further. And we are possibly going to be looking into computer vision AI for cable detection in images, similar perhaps to what you can see here on the left. And also we are planning to introduce some algorithms, possibly AI, to select which cables are optimal for recharging purposes. And then we are planning to produce onboard perception and navigation intelligence and putting this on board the drone. And so you can see more from our group at these links. And if you have any questions, you can write me a mail or you can write it in the chat. Thanks.
Thanks a lot, Nicolaj. I think this is very challenging. Wow, this is amazing. And your improvements are nice, really. So congratulations. Please remember that you can ask questions using the chat. You can already write the questions, and later in the final part for questions and answer, the presenters can answer the questions. Thanks a lot. And then this is the turn for Leah Matlekovic. Please, Leah.
Yes. Hi.
Thank you for coming, and please go ahead whenever you want.
Thank you. Okay, now you should be able to see my screen.
Perfect. Yes.
Great. Okay, so I'm Matlekovic. I'm here a PhD student at the University of Southern Denmark. And what I'm doing for this project, together with my team in computer science department, is we are building a microservices application for autonomous infrastructure inspection for drones for safety. You will hear more about it now. So the objectives of these applications are to build web interface, map-based web interface, where the user or the drone operator can plan autonomous missions. Then execute the mission and whatever is calculated to send to the drones, and the drones start executing the mission. And the operator can monitor the mission, how the drones are moving on the map. Also, when the drone finds faults or detect cables, we should be able to receive that information to our ground station or computer, whatever we want to call it. So another objective was to build like that application so that it is like modular and that it is scalable, because some parts of the calculations can be very slow if the application, if many users use the application at the same time. And we also wanted it to be easy to expand and change. That's why we implemented a continuous integration and continuous deployment strategy. So basically, when from developer side, when they develop the services, they implement new features, they just work on their computers, and when they push the changes to Git, it will start the automatic build and automatic deployment. It will containerize in Docker and then deploy to a Kubernetes cluster. And this is the architecture of our app. If you look at here, I will just briefly explain so that you know what is happening here. Let's say that maybe the most important part is like this part, where we are calculating inspection routes. First of all, we want the inspection route to be somewhere close to the infrastructure, like power lines or railway cables, power towers, or bridges. So here we extract all the information from OpenStreetMap, like where this infrastructure is located, and then we build a graph out of it. And we measure the distances between all the nodes in the graph so that we can use A-star pathfinder to find shortest ways. And then we are using a routing solver to basically solve a vehicle routing problem to determine like which drone should inspect what. And then the user from the web interface chooses which infrastructure should be inspected. This middle part is storage for the data received from the drones, or when the mission is planned, it is stored here in database, so the user can send or upload the mission to the drones, and then drones' local algorithms can take over from there. So the drone will receive global waypoints, like latitude, longitude, and start executing the mission from there, like fly point to point. And then the drone can report images or faults or videos back to the cloud. And here we have like a image analyzer, like to detect faults or fault types, maybe to do the 3D reconstruction of the infrastructure. And then we can use it for a more detailed path planning. And now I want to show you like how the route calculation works. So this is the prototype of our application. That's why it is only in Denmark. And when we zoom in, the blue dots are power towers. And I can select, for example, some power towers for inspection. The orange dots you see, those are drones. And for now, we are pretending that they are here, but we will test it first in a simulation, and then we will test it with real drones. And then when I press calculate route, it will calculate like which drone should approach which power tower. And if you have any questions, let me know. I will be happy to answer. Thank you.
Thank you very much, Leah. Very, very, very interesting. Not only people using Google Maps can travel with the interface, also drones can go directly to the point. Thank you very much for the contribution. And of course, you are very welcome to ask questions, please. This is very important. Thank you, Leah. So now the turn is for Liping Shi. And hi, Liping, welcome. It's your turn. You can start whenever you want.
Did you see my screen?
Yeah, perfect.
Yes. Yes, my name is Liping, and I'm a PhD student from Aarhus University. So the topic I want to present today is about the inspection path planning. It is a collaboration between the Aarhus University and the University of Southern Denmark. And next page, yes. So the problem we are trying to solve is basically trying to plan the drone to provide a waypoints, a list of waypoints, the path to guide the drone to navigate along the inspection target. It could be a drone, it could be a bridge, or it could be a power towers. And we assume that a basic 3D map of this inspection target is provided. And the method is a type of a combination of segmented voxel sampling, traversal path search, and sequential convex optimizations. And in this research, we evaluated this method on two inspection targets, the bridge and the power tower. And we also evaluated the computation characteristics. So what we considered inside this problem is a 3D map of the inspection area, and also the dynamics of the jumps, and as well as the limitations of the cameras, for example, the field of views and the focus length. And we consider these aspects and generates the path as an output. So the process consists of 3 blocks of computations. So we read the point cloud, and then we do some pre-processings to cleaning the point cloud and downsampling it, and then we generate a graph and search the paths afterwards. At last, we optimize the paths based on the constraints of the jumps and the onboard sensors, and at last, we export the waypoints with sense orientations. So this is an example of the first step. So we're cleaning the 3D map, and then we calculate the normal vectors of the 3D map and downsampling it. The second step, we segment the inspection target to, for example, the top side, the back side, right, left. Then we generate a graph for each segmented areas, and then we calculate a traversal path to visit all the sampled points. Then we conduct an optimization space following the limitation of the cameras. Basically, we convert the constraints, for example, the safety distance or the inspection distance, and the incidence angles of the cameras, those constraints to our convex optimization problems. And then we solve these convex optimization problems in a sequential way. Then we evaluate this method for two different use cases. First one is the bridge, and second one is this power towers. What we did extra on the power tower is we need recreate the surface of the power tower. Then we run the data processing chain following the method. The computation-wise, the most time consumption is used for the optimizations, and the other part is quite fast. And it is depending on the numbers of samples, the computation times is linearly increased. So the conclusion of this research, basically, we provide a way that trying to generate the path following the sequential convex optimizations, and we also provide a new traversal path search method, and we evaluate this method on both the power towers use case and the bridge inspection use case. Yes, I think this is all for the presentation, and if you have any questions, feel free to send me emails. And for more detailed information, you can also find in the attached paper. Yeah.
Okay, thank you very much, Liping. Very interesting, and I think this is somehow complementary to the path planning issues we face in Labyrinth, as you will see later. So maybe we can think of a stronger collaboration in the future. So nice, thanks for sharing your ideas and your work.
Yes, looking forward to your presentation as well. Thank you very much.
Okay, great. So now this is time for questions and answers. So you are very welcome to leave your questions on using the chat. And while the audience is getting warm for asking, I will do the first one. I will make the first question. This is, I mean, you in this context of the project, right? You mainly are thinking of a drone so that you can recharge using power lines, right? So any of you maybe can answer the question. The issues related to electrical isolation, right? Because you are approaching the power lines, and somehow the drone has to be prepared to suffer from, right, electrical issues, coupling with the structure of the drone. So how to manage that? Because the drone, first of all, physically has to be prepared, but also dynamically, in case some of the systems are affected by that, right? So have you tested these cases, and how is your approach prepared to face these kind of problems? Maybe you can answer, any of you or several of you.
Maybe I can take the first step here, and this way that's more.
Okay.
Yeah, so we had in the past some experiments with the drone. It's in fact like the drones of today, they are not designed to go to this area. Actually, they are designed to avoid this area. So when they see the high electromagnetic interference, the drone tries to stay far, because the navigation system will be highly affected. That is from the high magnetic field. So the AC lines, they generate 50 hertz AC current, and then that has a replication to the magnetic field around. So that is one aspect. The other is high voltage. So if you have 400 kilovolt and the drone operates in 20 volt, when it gets nearby, there is a discharge from the high voltage to the low voltage, and then you have the electric arc hitting the drone. Mm-hmm. We studied that, and we built a Faraday cage, so a protection shield around the drone. And well, that is still ongoing work to assure that we are like protecting the drone from any arcs coming from the lines. And this is one aspect. So we have to circulate all of the charges around the drone electronics. And in the middle, the electronics stands, so there is no charges jumping to the inner ones. So yeah, it's a concept of Faraday to make a kind of a jacket around the drone. For the magnetic interference, and the software side has to take care of that, because when we are very close, we see the magnetometer is highly affected by the magnetic field. So you see the drone is like going north-south 50 times per second. So that has to be somehow compensated. So our approach is to use the GPS at this moment. So we have a GPS antenna, so we use a satellite navigation system and completely block the magnetometer when we are very close to the power lines. Opposite to that, Frederik is using the magnetic field to navigate. So maybe Frederik, you would like to comment on that?
Yeah, so we're currently working in actually by equipping the drone with more magnetometers, trying to derive the position of the cables based on the magnetic field using inverse models of how the magnetic field fluctuates based on the number of power lines and also the phases of the current in the power lines. So you can sort of say that normally we talk about operating in a GNSS denied environment. We operate here in a magnetometer denied environment, but we try to use this to our advantage by actually navigating by the magnetic field generated by the power lines. Because here we are only interested in the drone's relative position to the power lines and not global positions. So in this way it will work. And additionally, to sort of normally we have the magnetometer in the IMU to provide the sense of direction for the drone. But now we can actually observe the cables and the direction of the cables, and then use this as our reference instead. So that is the general approach that we're taking.
Mm-hmm. Very interesting. Yes, of course, because it is clear that dealing with the real hardware, right, it is a huge problem. On paper, everything works in simulations, but later. So that's why I think, guys, you are doing a great job. So congratulations, everybody, on the project, and good luck with your PhD thesis. I am sure you will have very good results, and I'm wishing to share them with you in the near future. Thanks a lot.
Thanks.
I don't know if there are more questions from the audience for this project. Remember that you can use the chat or open the microphone if you feel more comfortable. We still have 2 more minutes for questions and answers. In any case, remember that the video will be available for everybody in the social media. So maybe we can expect more questions to come later when the sharing is wider. Okay, no more questions then? Okay, in any case, if later at the end of the session you are feeling anxious to question to do some questions, please do it. We have the long session for you to participate. Okay, thanks a lot, people from Drones for Safety. Welcome again to this session, and thanks for being here. Thank you very much. So now this is the time for Rapid. I am going to introduce the project overview presenter. Gerard is there, but James Riordan. I guess you are connected, right? So this is your turn.
Yeah, so I'm going to present on behalf of the Rapid.
Okay. Thank you, Gerard.
No problem.
Whenever you want.
So, hello and welcome to my talk on the Rapid project. So the Rapid project is a Horizon 2020 3-year project. It's 9 partners and it's €5 million initiative. The primary goals are to extend the operational capacity of drones to be able to complete infrastructure and maintenance inspection of large transport infrastructure within port and harbour setting. The underlying driver is that 1 in 10 bridges across the developed world are classified as being at risk of collapse. And drones are seen as the enabling technology to scale delivery of the services to enable fast and repeated inspection of these critical infrastructure assets. The project arose out of a use case requirement from the Hamburg Port Authority to be able to complete these inspections in a reasonable setting without having to close down the assets from public. Its final validations and demonstrations for the project will be completed within Hamburg Port area, as you can see. The Rapid project itself has a number of technological advances and developments running through, which are delivered by each of the 9 partners involved. The primary issue is that the port areas such as Hamburg are very large areas. The port within Hamburg extends over 40 kilometers, and it's difficult to be able to survey and deliver assets to the various points within the harbour and to cover the extent of the port. The delivery of the drones to the inspection area within the Rapid concept is being completed by an autonomous surface vessel, which can transit around the port area and carry a number of drone systems, which once on site connect as a swarm to be able to carry out the job at hand. The power extension to the drone is delivered through an onboard battery hot swap system. The inspection is carried out in a fully autonomous manner. Once the drones land back to the autonomous surface vessel, the battery hot swap changes the batteries. And then the drone is ready to take the next mission directives. The inspection mission itself is subdivided through a swarm task allocation algorithm. The identification of the cracks on the assets such as the bridge or the issues within the infrastructure are identified then in real time using an ML algorithm, which is delivered on board the drone itself. Once a list of cracks or issues have been identified and recognized across the survey area, another mission will enable a close quarter survey of these specific areas and develop high resolution imagery, but also a 3D reconstruction of scene of these cracks or issues. These very high detailed photos and 3D scenes will then be provided to a second automated algorithm for second level classification and danger, and also delivery to an expert analyzer through both an online platform and through delivery through development of a 3D digital twin. The payload systems which are being used across the Rapid program is both camera-based imagery, 3D reconstruction through photogrammetry, and 3D reconstruction through imaging LiDAR systems as shown. This is one of the bridge assets within the University of Limerick that we use for inspection and demonstration and development of our technologies. The inspection will also be analysed over time to identify large-scale issues within the infrastructures over time, and also to identify how these cracks or issues progress within the infrastructure over time. One of the development targets for Rapid is to also address the mitigation of beyond visual line of sight operations. BVLOS flight is mandatory for effective use within the Rapid project and also across many of the other future business models for drones. Drone operations are a relatively new entry into traditional airspace. Model aircraft and other radio control craft would have existed for many decades and have been allowed to operate up to 400 feet. Regulation of the airspace is critically important and in recent years have been harmonized across Europe through the European Commission and EASA. The current situation is that we must be relatively within visual line of sight, up to 400 feet operations and maybe up to about 800 meters distance, depending on the size of the drone and the visibility in the area. The current situation for all companies exploring BVLOS flight connectivity is that within uncontrolled airspace, they must have an operator or observer on site within VLOS. There is no real exception to this currently. If the industry is to become viable, then the industry must deal with the enactment and risk mitigation of the BVLOS flight itself, namely the loss of the pilot vision in the cockpit. The concerns that the regulators have often primarily associated with small manned aircraft such as Cessnas or search and rescue helicopters, and the risk associated with the collision of UAVs with these low-flying aircraft is we only have 100-foot separation between drones and low-flying aircraft in traditional Class G airspace. However, if future unmanned concepts come to fruition, then they will bring fleets and swarms of drones cohabiting and cooperating in clustered environments. And in this scenario, the risk of drone-to-drone collisions also becomes an issue. The loss of the pilot in the cockpit of the flying platform can, however, be addressed through new emerging technologies. In general, it won't be a single system which will mitigate the loss, but will be a number of factors, including unmanned management systems, detect and avoid systems, and transponder systems. Within the detect and avoid systems, the detect and avoid system need to be able to detect vehicle incursions into its airspace and also detect close range collisions during its normal flight. These include both ground collisions and also drone to drone collisions. Within the rapid concept, we are investigating a number of sensors for detect and avoid, including radar, LiDAR, infrared, and RGB. LiDAR can offer cleaner dataset and further ranges to that of the RGB camera dataset, whereas radar and infrared sensors can offer extended range detections. We utilize a scenario digital twin of the port of Hamburg within the rapid concept. This is built around the Unity environment, in which we have then augmented within the environment small flying objects such as birds and small aircraft and drones. We model the transmission receptive response of the sensors such as LiDAR using a high performance GPU ray tracer, and using the animation software we investigate the spatial and temporal variability of these imaging systems, focusing on flocks of birds at a number of iterations of the LiDAR scanning pattern. These simulations give us critical data sets in the development of the systems and help us evaluate the response to the varying scenarios. We operate at 2 test sites for the rapid concept, which are based being utilized for execution of the testing and demonstrations within rapid. The first, as you can see on the left, is located close to Dublin in Ireland and is a flight training area where manned pilots learn to fly effectively. So you can see the runway close to the coast here, and the pilots do multiple touch and go scenarios over this runway. We fly close to this, and we often fly in tandem within the circuit with the manned pilots. So we get both the capability to have data sets where manned pilots are flying close to the drones that we have, and we also have restricted airspace where other aircraft can't enter. And I guess this is critical if we're developing AI algorithms where we have some unknowns and we want exclusion airspace for it. The second test site is based in Hamburg, port itself shown on the right-hand side here. This will be the final demonstration of the rapid systems and will demonstrate all of the developed platforms and services. Within the real setting, this will be completed at the end of the project. So to move on to the more interesting talks, today I have 4 presentations, each of which are somewhat focused on the detect and avoid problem within Rapid itself. And I guess the 4 presenters will also look at the 4 sensor environments of LiDAR, radar, infrared, and RGB. At the end of the presentations, then we have a Q&A session, and we hope to have a good discussion around the project, the deliveries within the project, and also the platforms that we have under development. So I'll pass back then to the first presenter and back to the organizer.
Very interesting. I'm anxious to hear the speakers. So we will go directly with the first one, Alex Doe. Hi, Alex. Welcome, and this is your turn.
Thank you. Can you see my PowerPoint?
Yes, perfect.
Excellent. Okay, well, thank you guys very much for hosting us today. Thank you everyone for coming along, and thank you, Gerard, for that brilliant introduction there. My name's Alex Dow. I'm looking into AI-enhanced LiDAR perception for autonomous drone flight. with my supervisors, James Riordan and Santiago Matalonga. A little bit about myself. I've got a bachelor's in sound engineering and production. My master's is in digital signal and image processing, and I have a strong interest in artificial intelligence, computer vision, deep learning, and aerospace technology, which this project brings together quite nicely. So, how can LiDAR-based AI pipelines facilitate autonomous UAS flight? UAS being unmanned aerial systems. Well, in general, self-piloting drone technology will help us across many sectors, from commercial to emergency. But specifically looking at the port and harbour inspection issue, it's an urban environment. It's built up, and that really lowers the range at which you'll be able to not only see threats, but also the time that you'll have to detect small objects such as birds and drones, which could impact. One of the sensors that can be used for this kind of detection is LiDAR. LiDAR is very useful in this kind of area because, as you can see in figure 1, the drone is, we've got a mini Mavic there flying. It's a small drone. You can't really pick it out in the RGB, but you can see very clearly where it is, that little bit of yellow dotting around there in the LiDAR imagery. LiDAR, which stands for light detecting and ranging, produces hundreds and thousands of lasers a second. You measure the time of flight it takes for the laser to fire and return, and then you get an extremely accurate 3D image in the XYZ plane of centimeter accurate positioning for objects. So what's our proposed approach? Well, we're looking at adapting and exploiting technological progress in autonomous automotive driving and UAS surveying and mapping. So the AI pipeline is where we take things from the current state of automotive-based autonomous driving. So the current state of LiDAR-based autonomous driving is supported by data sets such as the Kitty dataset and AI pipelines such as point pillars. You can see here we have a point pillars processed point cloud in figure 2, and a nice little animation here of the Kitty dataset with some bounding boxes around the cars there, showing what this work is currently capable of doing. From the UAS side of things, we're using a DJI M300 as well as the DJI Zenmus L1 LiDAR system, which is currently something that's very commonly used for surveying and mapping, and bringing these two things together to allow us to venture into a new field for autonomous drone flight. Finally, we're combining that with the virtual to allow for rapid and safe testing. It will allow us to measure and understand these safety critical systems in a lot of detail, as well as conducting far more experiments far more often than you would usually be able to in the real world. To do that, we've got a hyper-realistic digital twin, as you can see there. Earlier on, you saw some pictures of the Hamburg model, but you can see clearly here the M300 is very well designed. And we're also able to produce synthetic data, which is going to be very key because we have to augment the data sets that are already out there. The automotive driving data sets don't have things like birds and drones in there. We'll have to produce those classes and insert them ourselves and then retrain our own networks. And we can do that with a synthetic version of the L1. As you can see there in figure 6, you have a 100 millisecond scan of a small plane using the L1. You can see quite clearly that it's a plane. Then we've got some upcoming field tests. So it will be expanding on the current testing that we're already doing in Kokno. And we'll be building upon other rapid testing near the University of Limerick. As you can see, this point cloud here from some testing near the bridge in Limerick. As was mentioned, Newcastle is an airfield in Ireland, and it's an opportunity for us to collect data of other drones and aircraft, of the other partners that are within Rapid and working with us. It also allows us to integrate our different aforementioned processes. So as you can see here, we have our own version of point pillars now running on our system. And we'll be able to use the simulated data, the work that we're doing on allowing for the detect and avoid capabilities, and we'll be combining all this together, and that will allow us to push forward not only our testing, but also this vital field of research for autonomous drone flight. That's it from me today. If you'd like to contact me, here's my email address, and I'm more than happy to answer some questions later on. I'm really excited for them. Thank you again for having us, and thank you for listening to me.
Thank you, Alexander. Very interesting, very well presented, by the way. So
thank you.
Congratulations, very nice. Okay, people, remember, you can ask questions. Don't forget that. And now it is the turn for Hector Arroyo. Hi, Hector. You're very welcome to start your presentation. I cannot hear you. Please check your microphone. It seems to be okay.
Yeah.
Okay, now, perfect.
Can you see my screen?
Yes, we can.
Sorry.
No.
Now.
Okay.
So good morning, everyone. Thanks for having us, and thanks for coming in to listen to us. My name is Hector. I'm also a PhD student with the University of the West of Scotland. My PhD is actually slightly different in the format because it's actually an industrial PhD, a collaboration between UWS and an industrial partner, CodePlay, which is a software company with an additional item to my PhD, as I will explain in a little bit. Just as a quick recap from what Gerard and Alex have said, because quite a bit of what they've said obviously applies to me. I'm focusing in the radar technology for the detect and avoid problem, trying to look into those objects that are a few hundred meters away from us and that are small and non-cooperative, so those other drones, birds, and things like this. And in particular, I'm looking into radar for some of its unique characteristics. So it offers usually a longer range compared to LiDAR, so you can get an earlier warning. It's also resilient to different weather characteristics and lighting conditions. So for instance, you can still use it to sense the environment in fog, in rain, and in the darkness, which can be obviously helpful. It has the feature of being able to capture velocity of objects. So this will be quite useful for obviously being able to discretize between different objects that are present in the environment for different moving characteristics. And then there's been a big advance in the field in the last few years, in the sense that the newer systems now provide much richer quality data, which means that obviously deep learning models are hungry for data, and this is really good for them to sort of make sense of the environment. So in terms of, I thought to show you guys quickly what does radar data looks like. So as you can see, it's not as dense as LiDAR data, it's more sparse. Similar challenge to that of Alex. We have to start with automotive because there's barely data in drones. So you can see a car here driving in the road, and you can see how it perceives the environment. The dots, you can guess the outside of the road, and you can also see other cars coming in. Those spikes there show the velocity of each one of the returns. So it's quite useful in that sense, just to discretize between different objects. And the point where we are wanting to get to is somewhere close to this figure here on the right, where we can label per point what each object is. So whether it's a car, it's a truck, it's a tree, and obviously move this away from the automotive paradigm to the drones and the 3D paradigm. To achieve that, I just put together some steps here that we're aiming to go through. So obviously, as I said, we're starting with the existing data in automotive. From the previous slide, then we will be looking to get our own sensor, which we do have, and augment this data that I showed you with our own data. So this image here, apologies for the quality, is from a few days ago. this is actual data from our own sensor here in Edinburgh, and you can see here those 3 cars approaching the junction, and you can see those 3 red blurs just there in the radar as well. So we will want to merge these 2 things together to enrich the data set that we've got from Automotive with our own sensor to make it generalize better. And then obviously one of the key challenges will be to move away from this 2D problem, which is self-driving. It's a road, is 2D, it's a 2D scenario to a 3D scenario with all the complexities that comes with that. Then we will need to start adding data in this 3D environment and labels representing the use case that we are aiming for, which is like obviously all the other drones and birds. And then we will move away from potentially first testing it in a static environment, so maybe a tripod with a radar and being able to see outside to test and deploy the solution in a drone. For the research journey, in particular my research journey, and considering the industrial partner as well. So having finished already the literature review and the problem research, I'm working my way through developing this custom algorithm that can take on these steps. The first step here, down here, aligns very well with the Rapid project. So it will be all the stuff that Gerard and Alex were talking about. I will be attending the field test to acquire our own data and be able to train the algorithms with it. The next step here is the one that aligns more with the industrial partner. They are a software company, and they are interested in moving away from the vendor lock that NVIDIA and CUDA has to a more open source solution, which is called SQL, and use that for GPU acceleration with TensorFlow. So I'll be looking to add this leg to the project. And this will be some sort of iterative process where obviously we will have different opportunities to acquire data, feed it to the algorithm, test the results, hopefully lead to publications based on those results, and then sort of start again, maybe complete a couple of 3 iterations through the PhD. I think that's it for me. More than happy to take questions at the end, and thank you for listening.
Thank you very much, Hector, and I wish you the best of the luck. Here in Spain, we also have this industrial doctorate format, so I think this is very, very interesting, and of course, direct contact with the with industry is another issue and very necessary. So congratulations on your PhD, and also the best of the luck, right, for you in your thesis. Okay, you have a question in the chat. Maybe you can get ready later to answer it at the end of the session. Perfect. Okay, now it is a turn for Mahammad Irfan. Hi, Mahammad.
Hi.
How are you? Okay, you're ready to present.
Okay, so
yes.
Can you see my slide?
Okay, great.
Good morning, everyone. This is Mohammad Irfan. I'm a PhD student at University of Limerick, and my PhD supervisors are Dr. Gerard and Dr. Peter Trislik, and I'm working on a Rapid project. My PhD research topic is based on autonomous navigation of unmanned aerial system, also known as drones in for GPS denied environment. So I'll be discussing all this in my upcoming slides. So nowadays we find autonomous drone in everywhere, every field of areas, starting from agricultural to medical to underground mining, different areas. So we are working on breeze inspection. You can see where GPS signals are weak. Most of the application we can see GPS, all the areas are GPS denied. Therefore, we are working on SLAM-based navigation. SLAM is basically a simultaneous localization mapping. It get the input from the stereo or RGBD camera and generate 2D, 3D point cloud map, and we can navigate a drone in GPS denied environment. So high accurate drone navigation is a very important task in drone application, despite in GPS denied environment or errors or drift in IMU. So applications such as building a 2D or 3D map of the environment, inspection of structures or bridges, indoor tasks such as warehouse monitoring, high accuracy of surveying, search and rescue mission, all these are the areas where GPS signals are very low. So a basic drone platform consists of basic low-level controller, stabilization with onboard autopilot and onboard IMU, a GPS or RTK system, onboard stereo cameras or RGBD cameras, robust communication system that may be a Wi-Fi router, add-on integration like onboard SDK.
Before joining to the session, please switch off your microphones. Thank you. Sorry, Mahammad, you switched your microphone off. Sorry. Okay.
Yeah, fine. Sorry. So add-on integration like onboard SDK, mobile SDK with API ports for building different kind of software algorithms like ROS, different payloads, RGB or LiDAR cameras or different types of sensors. So for drone navigation, when operating a drone in a GPS-based signal in a valley or a city, natural man-made environment or structure near the buildings or bridges, this GPS signal may block the satellite signal. So in another case, inertial measurement unit, IMU-based navigation and control system, it comprises a set of different sensors like accelerometers, gyroscope or magnetometers. It provides the drone with data on linear acceleration across 3 axes of measurement, that is pitch, roll and yaw. And there is a SLAM-based navigation system which we are focusing on. It provides position of the robotic agent as well as the map of the surrounding environment. Therefore, online SLAM is considered as best in GPS-denied environment. So you can see the DJI drone, which we are using the hardware platform with onboard integration DJI flight controller and IMU. It consists of stereo cameras in all the direction, a ground control system that is laptop, a companion computer which is we are using onboard NVIDIA Jetson NX, which integrated with ROS development software. With the use of DJI onboard SDK, we subscribe and we publish the point cloud, 3D point cloud, and various stereo camera output, scale disparity map, and you can see here in ROS visualization the 3D point cloud from the drone. So all these topics will be using as input of SLAM algorithm to generate the 3D map. So basically, a SLAM algorithm, there are different categories of SLAM algorithm. We are focusing on OBSLAM. It is able to communicate in real time in the camera trajectory, and it provides a sparse 3D reconstruction of the map in a wide variety of environment. It uses monocular, stereo, RGBD, and inertial cameras as the input. So SLAM is basically a simultaneous localization mapping. A drone needs to know its position in environment. So SLAM provides its position and it maps the environment. It is very much open source and compatible with ROS. It uses in GPS-denied environment, which are not previously explored. It uses extended Kalman filter, which is known as the heart of SLAM. So basically, SLAM uses vehicle's own odometry, that is drone's odometry, as well as the change in object landmark to estimate its own position in an unknown environment. So basically, for testing all the algorithm and the navigation algorithm or SLAM algorithm, it is necessary to test them on a simulator. Otherwise, testing them directly on a drone will result in its frequent crashing and damage to the drone. Therefore, we are using a DJI assistant. DJI provides is DJI assistant simulator, as well as ROS-based Gazebo simulator is one of the very interesting simulator platform where we can test our SLAM algorithm and different navigation or path planning algorithms. So here you can see the implementation of OBSLAM 3 with our drone onboard stereo cameras. You can see here we tested in our lab the SLAM algorithm. It can generate load the keyframes and it detects the key points of the lab, and it save in a txt file, and it create a sparse 3D map of the environment. So using this, you can see here. Yeah. So we constructed this map of using stereo camera, and this is the result of the stereo camera SLAM map. We can use this map as later at the path of path planning, and we can implement different kind of navigation algorithms such as A*, AFP, and different. We are also focusing on stereo inertial and RGBD inertial SLAM implementation, and in future we are will be working on fusion of camera or LiDAR, and will generate other SLAM algorithm as well. So thank you. That's it. And if you have any question, you can ask. Thank you.
Thanks a lot, Mahammad. Thank you for your interesting presentation. Remember, guys, that you can ask questions through the chat, okay? Now, this is the turn for Matheus Santos. Okay, here we have it.
Yeah. Hello.
Hi,
Can you hear me?
hello. Yeah, perfect.
Yeah,
so you can start. Thank you.
Hi everyone, my name is Matheus Santos and I am a PhD student at the University of Limerick, and I am under the RAPID project, and my PhD supervisors are Dr. Gerard and Dr. Petar Tislich. So in this presentation, I'm going to give you an overview of the progress we have made during my PhD, and the title of the presentation is the long-range detection in aerial infrared images for sense and avoid system. So first, the unmanned aerial vehicles market was evaluated at 30 million in 2020. So we can see that we have many interests in this market, and UAVs that has the potential to be used in many important sectors, such as entertainment, agriculture, security, and infrastructure. And the automation of these tasks has been targeted by researchers in the recent years and should become a reality soon. However, when we are moving for UAV pilots who has visual line of sight to remotely operated systems beyond visual line of sight, it has a significant risk associated with it. And one of the most important risks that UAVs face and pose is the mid-air collision. That's why when we are developing automated systems, we need to provide a good detect and avoid systems that are able to perform actions to maintain a distance to other aircraft and also to avoid a collision. And the first step for such a system is the detection of other aircrafts in their airspace. In order to perform the detection in our system, we first perform a shape recognition by using machine learning techniques. And to do so, we have input data and data set that we're going to extract features from this data, and then we're going to train a network from this data, and then you're going to create a model that's going to be used for real-time applications. However, the current data set doesn't provide us much information about flying planes, flying drones, and infrared images. And that's why we recorded our own data set. And from this data set, we trained a smart network based on the YOLO5 algorithm. This algorithm divides the image into regions and then predicts bounding boxes and probabilities for the object detected. Here we can see in the left side the wide angle camera for the data set, and at the right side the infrared images and the detection of the network that we trained. The YOLO stands for you only look once. This means that the prediction in the entire image is done in a single room, which makes the algorithm fast and applicable for real-time applications. But when we are dealing with long-range detection, we can see that sometimes the aircraft, it's close to a small dot on the image, which make the network to learn how to recognize dots and not really the shape, because we don't have that much information on those detections. That's why we are incorporating in our object detection a second component, that is the motion estimation, by applying a technique known as optical flow. The optical flow estimates the movement on the image, and there are two manners to compute the optical flow. The dense optical flow, when you compute the movement through all the pixels of the image, and the spatial optical flow, when you choose just a few points to tracking those points. And the approach we are proposing now, we are fusing the information from the machine learning with the spatial optical flow. So we use the object detection by the neural network to feed the spatial optical flow. So we first get the image, then we apply the detection by the neural network, and then we have both the object detection, but now we feed the spatial optical flow, and then we can fuse this information in order to improve our detection. So here we can see an example with our data set, when at the left side, we're going to see the machine learning and the spatial optical flow separately. And so we can see here in the blue square, the machine learning performance. So we have some outliers being detected, and also the spatial optical flow following the plane. And at the right side, it's the fusion of the information. And we can see that even though we can detect here some false positives because of the noise of the image, the fusion of the information makes us to overcome those problems, and then we can reduce the false positives in our estimation. You can see that basically when the camera moves, we add some much noise on the image, and then we have some problems with the detection. But when the model that we are proposing, we can overcome such problems. So what we have achieved so far is that we can improve our detection, so we can reduce the false positives, and we have a model that incorporates different features. So we are merging the shape recognition with the motion estimation, and also we have a real-time applicable approach, because YOLO is also fast, and the spatial optical flow we are just applying on the selected point, so it's also a fast approach. So this is this makes the approach to be applicable in real time. So that's it for me. Thank you for your attention.
Thanks a lot, Matheus. This is amazing. I think this is a great contribution to the project. Congratulations on that. And okay, this is now the time for questions and answers. So here we have 2 questions in the chat. Please feel free, any of you, to answer the questions. I think the first one was for Alexander, if I remember well, or I don't remember exactly what time.
For me, probably.
I think it was for Hector for the radar sensor.
Yeah. Thank you. Okay, so go ahead.
Yes, so Nicolaj, we are using a millimeter wave radar as well, same as you guys, I believe. It operates in the 77 to 79 gigahertz band. It's got a range of up to 350 meters. The maker is Oculi, and I can send you the details if you want after the chat, and you guys can have a look.
Okay, thanks a lot, Hector. Nicolaj, if you have extra questions or you want to comment on the answer, perfect. Okay, nice. Now we have another question from Blanca. So apart from the sensing and detection stage, are you also working on the avoidance stage? If so, what are or your approaches to this matter?
So for us, we are still just focused on the detection. We're not working yet with the avoidance approaches.
Okay.
From our side of things, there are other parties within the research lab currently looking into the avoidance stage, and hopefully down the line, the aim is to bring the sense, detect, and avoidance all together.
Very nice. Thank you guys for answering. There is someone who raised the hand. Let's check who it was.
It is me.
Yes, please. Go ahead, please.
I have a question for Irfan, but in general for all of the guys that are working on Islam. Islam is complex to do with high precision, particularly along flying, but the quantity of information in general in the SLAM after you build the map is very high. It is excellent for a person that is looking at the map, at the SLAM that you have built. The question is, with this model, once you have built the SLAM, are you going to try a secondary step or to extract some semantics from it, or to recognize particular elements and to organize in a topological or semantic map, something like that? Have you considered this for the photo?
Okay, so we are planning for the navigation part, that is from using this map from the OBSLAM will be approaching different path planning algorithms like A star or AFP for the navigation.
I'm not speaking specifically in navigation, that for other purposes, like, I don't know, you are trying to go to a place and you need to locate something in the scene. Are you going to augment this map, this SLAM map, with other semantic information, or is not considered, and only you use the map for navigation or for path planning or whatever?
We are not, like, for semantic, we have not planned yet, but yeah, for navigation we'll be doing this.
Yeah. So just to add into that, I guess in terms of the SLAM part within this project, it's primarily focused on GPS denied and cluttered environments around urban areas and whatnot. It's just around the navigation localization. We are doing some semantic stuff for the identification of cracks and issues within the infrastructure. So this is another partner. It's Thales are delivering the semantics around the crack detection, and then we utilize that crack detection, those semantics, to identify, a location where we need to do a close quarter, high resolution survey around that crack. So there is some semantic stuff going on within the project, but it's not directly related to Mahammad's work.
Okay, thank you.
Just as another note to Blanca as well, if you have any specific questions or you just want to be put in touch with the team that's maybe looking a little bit more into the avoidance stage at the moment, feel free to email me or get in contact. I'm happy to put you through.
Thanks a lot, Alexander. Okay.
There is another question there from Javier. I think.
Yes.
I can maybe take that one. So you're absolutely right. The data sets are recorded from the front bumper of the vehicle, so you are really perceiving, even though what you see is from the top view, the bird's eye view, what you're really perceiving is the front of all the objects. Then when you move to a 3D environment, what you're actually going to see is the top of the object. So there is a big task there to move from one scenario to the other, and it's a task, a research area on itself, which is called domain adaptation, and that's just that can take up a whole PhD on itself. So it's potentially an area of research, and is definitely a challenge that we will need to look into.
Yeah, even looking at the AI networks that kind of build off of these data sets, you look at point pillars, for example, and many of the others, they're looking at on the Z-axis, they're only looking -1 to 3 meters. Whereas in terms of UAS flight, you're looking at, you want to have a much wider view range than just 4 meters.
Thank you very much, guys, for the answers. I think everything is solved. Okay, great. So we are now, according to the agenda, we have a break because until 11:10 we don't have to come back and start Labyrinth with Labyrinth project. So I think it is good if we fit the agenda. So in case anybody is joining us later at that time for the following project. So if you all agree, we are going to stop recording right now. We pause the recording, and in 30 minutes maximum, we will be back, and we will start with the last project, Labyrinth, and the last part of the session. Of course, in the meantime, you are also welcome to leave your questions in the chat, and your questions will be solved later when we are back. Okay, so please be participative, and we will wait for you in 30 minutes. Thank you, guys. Hello, everybody. Welcome back. We are just 1 minute ahead the next presentation. So this is the time to go back to the session and be ready for the last stage, right? So in 1 minute, we are starting again. In the screen, you can see the agenda. This last part is for the Labyrinth project. I will be responsible for presenting the project overview, and then later we will have 4 speakers, 5 minutes for each presentation, and the final round of questions and answers. So welcome back, and I will start in 30 seconds the presentation. I will share my screen with you. Okay, now it is the time. So I'm going to share my screen with you. Hopefully you can see the presentation now. So I'm going to share in 5 minutes with you the overview of the Labyrinth project. This is the last project participating today in this webinar. The IP is Professor Luis Moreno, as you can see in the slide. And also we have the Ruben Garcia as the technical coordinator from XSpace. So very briefly, I will comment on the main objectives of the project, which the main one is to create and validate new swarm drone applications to enhance safety, security, and efficiency in the civil system transport. This is the main objective, and for that we have a consortium, as you can see in the slide. And well, in case you have any questions or any comments to address to each of the partners, you are very welcome. You have the additional information in the project website that you have here, direct access to that, okay? And well, going directly to the sub-objectives of the project, they are summarized as followed. First of all, one main objective is to eliminate in controlled environments the need for drone pilots, right? To control the swarms. The idea is to control up to 10 drones through a new autopiloted technology. So this is leading to automatization of the drones, right? So also a second objective is the validation of drone swarm pilot services in a seaport scenario. We will see now these different scenarios we are managing in this project. Then we want to validate drone swarm pilot services that may lead to improved efficiency of road traffic transport surveillance operations. This is also a very important issue to address in the project. Also, we want to validate drone swarm pilot services in an airport scenario. And then another issue here is the improvement of the efficiency and the support to emergency situations, right? Assistance operations in urban areas. This is another important topic addressed in the project. Also, we want to achieve progress in accelerating the European Union's regulatory adaptation and public acceptance. As you know, people working on these kind of projects, this is a main issue here, regulatory adaptation and public acceptance, so that the real technological advances can really become a reality. Otherwise, this is difficult to manage. And then also analyze and propose new business models related to the diversification of the Labyrinth to other sectors and applications. So these are the main objectives. Here you have a summary, a picture of the main issues to address in the project. In the center, you can see the 3 main important topics we are dealing with, and we will show you the advances and the challenges we are addressing right now through the 4 presentations coming. But mainly they can be summarized in these 3 main topics, which are path planning and path control from UC3M and DLR. Also 5G communications, which is an important topic from TID and UC3M, and also cybersecurity from AIT. Okay, so these 3 main blocks are from a research point of view the main ones to address, and also of course they are affected by standardization and certification aspects, as you can see here, also regulatory aspects and project management. This is of course these all elements are feeding the research structure, and also of course very importantly the transport users cases. So for us the use cases are very important, and we have the 4 we are presenting in the next slide. So we have first, as the first case scenario, we have the road transport pilot. And you can see here that this is the road with the traffic. And the idea here is to achieve the following objectives. For sure, we have a speed control, vehicle distance measurement, plate identification and vehicle tracking, and traffic counting and traffic monitoring. These are the main issues to address in this main scenario. Later, through the presentations, we will see in these type of scenarios the advances we have addressed and achieved in the project. Then we have the case scenario number 2, which is a waterborne transport pilot. So here you can see a draft, a scheme of the scenario in which drones are there acting or supporting vessels inspections, for instance, seaport infrastructure monitoring and also surveillance, and dragging operation monitoring. So again, later we will see how the research approaches are driving us to obtain these or to meet these objectives. Okay. And then the last 2 scenarios, we have the air transport pilot in an airport mainly, in which, of course, we have to face bird scaring, pavement or infrastructure inspections, airport surveillance to avoid unauthorized access from external drones, people, whatever. Okay. So also the last one, which is the emergency pilot, in which, of course, well, imagine this is the picture in a concert, why not, with drones and ambulances and people in the surroundings. So surveillance operations have to be addressed, identification of casualties, escape routes, points of medical assistance, potential risks, and also communication with medical assistance services and coordination of the transport to the casualties. So this is these are the main four cases, use cases that we are addressing, And we will see now in the presentations how we are facing the main problems to achieve the operation, automated operation of the drones in these environments under these circumstances. Okay, so this is all from my side, and now give the room to the next speaker from Labyrinth project, which is Víctor Sánchez. So Víctor, welcome.
Well, hi, hello.
Hi, welcome to the session. Now you can share your screen and your presentation with us. Thank you.
Okay, can you see my slides?
Yes. Okay,
well,
great.
So, hello everyone, my name is Víctor, and today I will be presenting the paper entitled Multi-Interface Network Framework for UAV management and data communication. In the following slide, you can see the list of authors of this article and also my contact information, just in case you want to discuss further about this topic. Well, so due to the limited time that we have for presentation, I will directly present the communication architecture of the Labyrinth project. As it can be seen here, there are three main domains in the architecture that are the UAV domain, the ground control station domain, and the UTN domain. A simple mission results in the following procedure. At some point, the ground control station operators send a request to the UTM to start a mission. The UTM requests this and if everything is feasible, if everything is possible, it accepts the mission and sends back the authorization to start the mission to the ground control station with, for example, different information like the path planning. This information is checked again in the ground control station by the operators, since they are the main responsible for maintaining the safety and the security of the mission. Once the UAV is in flight, reports must be sent periodically to the UTN from both the domains, the UAV domain and the ground control station domain, and these reports may include essential flight parameters such as the UAV position, the GPS position, or the UAV battery. So UAV domain and ground control station domain have connectivity to the public network, to the internet, either using the satellite or cellular network. The best case is 5G connectivity, but it can be, for example, 4G or any other cellular connectivity, in order to perform this periodical transmission, these periodical reports. Well, so with this in mind, we know that the traditional way to connect the UAV and the ground control station domains is by using a radio frequency link in more professional environments, or maybe Wi-Fi in domestic or recreational environment. But taking the advantage of the fact that both domains had to be connected to the internet in order to make these reports that I mentioned before, we enable the communication between both domains using these 5G technologies, allowing by doing so the beyond line of sight communication between both domains. Well, so in order to test that, we decide to take like an experiment, a preliminary validation of the communication, and for doing that, we have decided to use the UAV and the ground control station domains. In this validation, both domains communicate using three alternatives: the public network, the internet, the Wi-Fi, and an emulated radio frequency link using the venue emulation platform. A VXLAN, a virtual extensible local area network that you can see here, has been created between these three alternatives, which is an overlay protocol which allows different domains to be connected as if they were in the same local area network, regardless of the elements that are between them. So the changes between the communication channels are then made by attaching this VXLAN to the Linux bridge that you can see here in the interface manager. At this moment, the changes between the channels and the links are made by an operator in the ground control station, but we are working right now to migrate this interface manager in an automatical procedure in order to select the channel based on different network parameters such as the delay, the available bandwidth, or maybe the packet losses. It can be anything. So, as can be appreciated here in the following graphs, the telemetry, in the experiment, in the validation, we are transmitting a telemetry from the UAV to the ground control station, and we are changing the link just to see if everything is working as expected. So as can be appreciated here in the following graph, the telemetry that is received in the ground control station monitor is stable and is always working regardless of the limited interface that they are using to communicate, which allows...
Please, Paula, please could you... Okay,
okay.
Thank you.
So, okay, so as I was explaining, this ground control station monitor is receiving the information regardless of the interface they are using to communicate. And in the right side of the image, we can see the same information, but this time captured in the communication equipment. So we can see that at some point, this information was received using the radio modem, at another point received by Wi-Fi, and other time received by the 4G LTE connectivity. So this work serves as a starting point for designing the communication architecture of the Labyrinth project. So thank you for your attention, and if you have any question, we can discuss later.
Thank you, Victor. Very clear. Nice. Thanks for sharing your ideas and your work with us. Okay, people, remember that you can use the chat or open the microphone directly if you have questions, but keep them until the question and answer moment, right? At the end of this part. Okay, thank you. Then this is the turn for Luis Felix González, also from UC3M. Are you there, Luis?
Yeah.
Yes.
Yes, hello.
Okay, hi.
Okay, so can you see the screen? Great. Okay, so my name is Luis Felix González Blázquez. I come from UC3M as well, and we are going to see in this brief presentation about one of the research lines that we are doing in the Labyrinth project, which is the comparative study of virtual infrastructure management solutions for UAV networks. Now, first of all, we want to address the motivation that we have behind this research line, which is basically allowing the automatic deployment of different softwares and services on UAV platforms throughout the power of virtualization. But first, what is virtualization? Virtualization is basically the softwareization of all the networking functionality and services so that they can be softwareized or be delivered as software instead of having to rely on expensive specialized equipment that is difficult to sometimes onboard in some kinds of UAVs, as well as expensive to maintain. So instead, we want to aim to the softwareization of these services so that they can be deployed in more generic hardware that is much easier to maintain as well as to operate with. So using virtualization, we are able to reduce the development cycles because, after all, we will be dealing with software just as if we were dealing with programs instead of with hardware. And also, all of the cycle of product, like for example the testing and the deployment, will be much easier to produce as well as to speed up this process. And also, in the case of experimental scenarios, we are able to speed the validation and testing process because if something goes wrong at some point, then it is much easier to redeploy again all of these services rather than having to roll back in the hardware itself. And also in production-like environments, we can support the automatic deployment of all these functionalities, right? So we are able to deploy them automatically once an infrastructure has been set up. Some examples of these functionalities can be seen in, for example, a path planning service in order to see where the UAVs are going to go, network route configurations in order to deliver traffic using other UAVs or using the cellular communications, and a long list of functionalities can be exploited using this power of virtualization. Now, in order to see this idea better, we can see a very simple example in the scenario that we have here in the screen, where we deploy a path planning functionality over a simple UAV network, where they are interconnected using Wi-Fi. Now, due to the limitations of the Wi-Fi, and imagine, for example, in a scenario that there's no cellular connectivity available, to the ground control station, the UAV might not be in reach with each other when we deploy the infrastructure. So in order to send the information coming from a ground control station where a program is running in order to compute all the different routes that the UAVs are going to use in order to move and plan the trajectory that they are going to follow, a relay function might be necessary in order to send that information through another UAV, right? So as you can see in this case, the ground control station with this softwareization is able to deploy all these different services automatically once the infrastructure has been deployed, and then send information not only to the UAV that is able to reach directly, but also to a second UAV present farther away that is not able to reach through this first UAV that we have seen. However, in order to perform this functionality and in order to build this service, all these different relations and links must be able to be created between the services, right? So, for example, the path planning function, the path planning must be able to reach one of the UAVs throughout a link, as well as build the different links for the relay function in order to reach the information on the other side. However, in order to do all these different links and to provide the provision, we need to manage all of these actions, and because it's not so simple to perform. So what we did was to see all the different alternatives that we have in order to manage the deployment and orchestration of all these different services, seeing which one of these platforms was the most suitable candidate to be used in this kind of scenarios and for the Labyrinth project. And as we saw some of these platforms, including all of the characteristics that they provide, and we focus on 4 precisely: in OpenStack, Kubernetes, K3s, which is a light version of Kubernetes, and finally Eclipse Fogo 5. Seeing that Kubernetes, due to its high maturity as well as all the different functionalities that it provides, it's very simple to use, and it's very fast to have a cluster deployed over an infrastructure, as well as all the functionalities that it provides for the deployment of services. We saw it as a very good candidate for its implementation on this kind of platforms. Okay, you have more information about this comparison that we perform and how we see that Kubernetes is a very interesting solution in the paper that you see on the publication you see on the screen that is already available, and you also have on the screen some of the additional information for the virtualization in UAVs in this kind of scenarios in the papers we have on the screens. Nonetheless, if you have any questions, I'll be delighted to answer them. Or if you have further questions when this seminar is over, you can contact me in my email address that you have at the top of the screen. Thank you so much for your attention.
Thanks a lot, Luis. Very interesting. I think the order of the presentations are correct in the sense that the functionalities you are presenting, they allow the path planning that we are presenting now, right, through Blanca, right? The path planning running at a lower level can be later implemented really through communications and in an organized way, so that this is achievable by the swarm or the drones, right? So thanks a lot. Now we have Blanca Lopez. I can see you are ready, so go ahead.
Yes. Can you hear me?
Yeah, perfectly well.
Okay, so, well, first of all, thank you, Concha, for your introduction. My name is Blanca López Palomino, and today I'd like to introduce you to what has been my work for the Labyrinth project, which I titled Traffic Management and Path Planning for UAV Swarms. As Concha said before, one of our main goals of the project is to eliminate in controlled environments the need for drone pilots to control swarms of up to 10 drones through a new auto-piloted technology And the environments we have focused on are urban environments, which include road transport areas, waterborne transport areas, air transport areas, and we are also considering emergency situations in crowded environments. The specific real scenarios we are working with are listed in this slide. And here on the right, you can see a simulated map of the Santiago Bernabeu Stadium area. These simulated maps we are working with are obtained through LiDAR data and have a resolution of 5 meters. So to obtain this autonomous non-piloted navigation for the drones, we have divided our work into 2 big modules. First, the path planner and then the path controller. The path planner aims to get a global path from an initial point to a final point for a drone to follow, avoiding the environment obstacles. And then the path controller is in charge of detecting conflicted situations between drones getting too close to one another and resolving these situations. For the path planner, it is based on the fast marching square path planner algorithm, which main characteristics are listed in this slide. It is important to highlight that the way this algorithm gets the path is based on a viscosity or velocity matrix, which intrinsically takes into account the distance to obstacles. So it guarantees that the path obtained is smooth and it's safe away from obstacles. And it is also important to notice that in this viscosity matrix, we can add some restrictions we want the path to meet, as I'm going to show later. And this is relatively easy to introduce. So the types of mission we have considered are go-to-point or individual missions, that are the missions for a drone to go, as I said before, from an initial point to a final point, and then coverage missions of a certain area. One of the restrictions I was talking before is the imposition of a flight level, as you can see in the image below. It depends on the flight direction of the drone, and it's for ease to, and it's excuse me, I'm a little bit nervous. It's to ease the traffic congestion of the drones. Another restriction we can add is the possibility to add some blocking or some areas we don't want the drones to be flying by. For instance, in this image, we can see that drone 6 is forbidden to fly over this red square area, so it has to surround it. And other things we have been working for the path planner are that we have developed some simplified path planners based on the same fast marching square algorithm to ease computational time. For instance, we have developed a path planner that reduces the 3D path planning problem to a 2D path planning problem by projecting all the obstacles in a plane, and then the height of the path is reconstructed. And for the path controller, we have developed 3 strategies. First, the speed control, which identifies if 2 drones are getting too close to one another. In this case, one of the 2 drones has to stop its flight while the other one continues. And when the safety distance is restored, the stopped drone resumes its flight. Another strategy consists of blocking previously planned trajectories. So no other new trajectory crosses the previously planned trajectories. And finally, what we have called the conflict strategy through which we predict at which time each drone will pass through each waypoint of its trajectory, and a certain safety area marked by these blue cubes, so no other drones flies at the same time through these same areas. And that's all for my part. Thank you for your attention.
Thank you very much, Blanca, for such a great summary of the approaches. Very interesting. Thanks a lot. And this is for sure complemented with the presentation by Javier Muñoz coming next on coverage. Hi, Javier. Are you there?
Good morning, everyone. Can you see me? Can you hear me?
Yeah, perfectly well. Welcome.
Okay, I'm gonna share my presentation.
Yeah.
Can you see it?
Yeah, here you are.
Okay, so good morning. My name is Javier Muñoz Mendi, and I'm gonna be talking about coverage path planning for teams of UAVs for the Labyrinth project. The objective set in this project include two types of coverage missions: a linear coverage given a set of waypoints and an area coverage. Both these missions need to have collision avoidance capabilities and to be able to fly in a formation in the case that one UAV is not enough to collect the necessary information. The main objective of the coverage missions is to make inspections of certain zones, as my partners have explained, in the map to provide information to the authorities. For the area coverage, we select the longest edge of the target coverage area, so the coverage path has the minimum number of turns necessary, and then we perform back and forth motions to generate the initial coverage path. Since this path doesn't take into account obstacles, we then use the fast marching algorithm to generate a collision-free path, avoiding the obstacles that are at the predefined flight level. For the formation planning approach, we use a leader-follower approach with a triangle-shaped formation. To avoid obstacles, the followers get closer to the leader's path based on the values of the velocity map that my partner Blanca explained before. That means that if the formation gets close to an obstacle such as a building, for example, the follower UAV that is closer to the building will move closer to the center of the formation. That means that the follower UAV will then avoid all obstacles since the leader path is obstacle-free. Here are some examples of both the coverage area and the linear coverage using a team of 3 UAVs. For the linear coverage, the red crosses indicate the waypoints the paths have to pass over. This is useful, for example, to inspect streets and roads. The paths are calculated in 2 dimensions to reduce the computational cost according to the set flight level. The white pixels in the images represent free space, and the black pixels represent obstacles. As it can be seen in both cases, all the UAVs avoid obstacles successfully. To obtain the 3D paths, we calculate the floor level data of each map by getting the minimum height value in a row resolution grid. Then that value is added to the flight level value we predefined to obtain the 3D paths. Here is an example of an area coverage mission with a team of 3 UAVs in the Valencia harbor. The same procedure applies to the linear coverage mission. Here you can see an example of the linear coverage mission in the Bernabeu metropolitan area in Madrid. If you need any more details about the algorithms used to perform the coverage missions, you can check the following open access publications. And then to finish my presentation, I'm going to show you a short video of our progress with the planner so far. The video will show paths for 10 UAVs calculated in real time. One of them will perform an area coverage mission, and another one will perform a linear coverage mission. The remaining 8 UAVs will perform go-to-point missions with randomly generated start and end points. The red and yellow volumes represent the no-flight zones, meaning that no UAVs can fly through those zones. The red volume indicates a strict no-fly zone, meaning that no UAV can fly there, and the yellow volume represents a softer restricted fly zone, meaning that UAVs will only fly through if it is absolutely necessary. Then the path controller developed by my partner Blanca is used to avoid conflicts between the UAVs. And that's all for me. Thank you very much.
Thank you very much, Javier. Very
nice. If you have any questions, we can answer them now.
Yeah, of course. Thanks a lot, everybody, for presenting your progress, your solutions to overcome or to face the challenges of Labyrinth project. It has been very interesting. Thanks a lot. And now this is time for questions and answers. We have one from Joaquim Ramos in the chat. How do the different beams deal with drones possibly losing connection? I think this is more for Luis.
Yeah, I'll put the camera for that. So, yeah. Okay, so regarding how beams deal with the drones possibly losing connection, well, we did some exploratory work on the comparison that we did for all the different beams that were explored. In this case, we have more information about how they deal with OpenStack, Kubernetes, K3s, and Eclipse Fogo 5. And the thing is that with OpenStack, they deal with the intermittencies of the drones, at least in terms of connectivity, fairly well, especially taking into account that this was not a solution that was designed for this, because they are able to reestablish connectivity even though the connectivity might be lost for some time. It is able to reestablish the connectivity, but it has its own fair share of problems in that regard, because it's not only a matter of connectivity, but also let's imagine that the UAV needs to be replaced due to a battery replacement. All the services and functionalities that are running on a UAV need to be migrated. And this is where OpenStack falls a bit, because once the UAV place, all those functions need to be migrated, and OpenStack does not natively have any way to migrate easily all these different functionalities. So even though it deals with that kind of connectivity fairly well, it has that issue, as well as also it's a very computational demanding resource. So maybe some UAVs might not be able to have to onboard the necessary resources to have this. So this is the reason why we wanted to explore more the way of Kubernetes and also K3s, because K3s is more of the, let's say, the least it needs less resources than Kubernetes in order to deploy these different services, and also Kubernetes provides much more flexibility for the migration of all the different aspects, because once a UAV might be fault, you can program it fairly better in order to deploy all those different functionalities in another UAV. The thing is that for the connectivity is also we're exploring ways to reestablish connectivity better, because Kubernetes, due to its networking model, it provides more of a flat networking approach, which is a little bit more difficult to operate with, especially if you need connectivity between different services, especially if they are network related to the networking aspect. So there's also that part where we are now working on. Especially. And finally, then we have also the Eclipse Fogo 5, but the Fogo 5 we're still seeing how it's getting developed, because it's still on a fairly early stage. So right now, even though it has the ability in the future to have actually a distributed approach to orchestration and how they manage to with these connectivities, which in turn, thanks to its distributed approach, it would allow the different UAVs to not be an issue. The disconnections is still in a fairly early stage, so we're still seeing how it develops in order to do more exploratory work on Fogo 5. So these are we're still always exploring for new alternatives and possibilities to include in this kind of platforms. But for now, how each one deals with the disconnections, these are the ones that we have more information. If you want more information, Joaquin, actually, we have the paper that I've showed before, which I can share with you if you want, has more information about how each one of them deals with these problems regarding the connectivity, especially in this kind of platforms, especially on all the issues that plague these platforms. And also, you can send me an email and we can discuss about this in more detail if you are interested on it. But thank you for answering. Really good question.
Thank you very much, Luis. Joaquim, I guess your question has been solved. In any case, of course, you remember that you can contact directly with the team, with the speaker, and also we can share the papers with you, with the audience. I think it would be a good idea also to have access to the links for checking or viewing the different papers, open source papers that we have on the topics. It would also complement the video, if possible. We will try to do our best so that all this information is available for you during the in the web pages of the projects. Okay. Okay, great. Thanks, Joaquim, for asking. And there is now time for more questions in case you are wanting to ask more questions, or in case you have comments to add to the presentations already presented. Leah?
I also have a question for Luis.
Okay.
I see we are doing like very similar work, deploying K3S and playing with services. How do you see like drones as a part of the cluster? Like, would you think of deploying, installing a Kubernetes node on the drone and then just like make it part of the cluster? Or do you just think to deploy services somewhere like in Google Cloud or your own servers and then send the message to the drones, I don't know, HTTP or some other maybe more asynchronous protocols? Or do you have any thoughts about that?
Well, yeah, fairly. I saw, yes, that we are doing fairly similar things. To be honest, for us, we see that the own networks that we are dealing, because we are used to deal with ad hoc networks, we consider these networks as the cluster itself. We are deploying each one of the aircrafts is a node of a Kubernetes cluster, and we deploy the different services on the UAVs. Naturally, as I have mentioned in the previous answer, it has a fairly problem in this kind of scenarios because a flat networking model that Kubernetes uses for because it's more a cloud-oriented solution, and this connectivity is not something that is expected. It's more that the services might get deleted or might be moved, but not these connectivities of nodes itself. So we need to deal with this kind of communications because, well, basically a flat networking model on an ad hoc network is not the best approach, especially because when we have connectivities, then some UAVs realize everything into the protocol that is going through the network. So we are actually developing also a networking solution as a service for Kubernetes, so that all the different services and functionalities that we deploy in the network are going to they can communicate at the link layer level. So they have direct connectivity between the services and not relying on the Kubernetes itself and the API that they use usually, because they connect at the application level usually. So this communication, this solution that we're using is called L2SM, and we have actually accepted one work in IQ Network Journal on a special issue. So if you're interested, you can ask about this paper. So that because it provides far more details about this solution.
Yeah, I would love to
how
read.
we deal then with the exactly. So it has been accepted already, but
how can I
then
find
once
it?
it's on. The thing is that this has been accepted but not yet published.
Okay.
So
okay.
it still needs it, but
I will
it
have
has
to
already
read.
been accepted. And
Yes,
well, you
I
can
was thinking
you can
about
contact me
similar-
also through email. Yeah.
Okay, great, cool. I was also thinking about putting some nodes on the drones and how would communication works. And we had that problem that, for example, if we send the drones to autonomously inspect the infrastructure, basically they would change the IP. So even if you put, I don't know, nodes, even if you put node, you will not, you don't have the connection to the rest of the nodes in the cluster. Okay, thanks. I look forward
exactly
to
with
reading
this.
that.
Exactly with this, you will have that. You can mitigate that problem, because in that sense, all the connectivity, you will have control of it, and the communication is at the layer 2. So you don't rely on the network fabrics that you usually use in Kubernetes, like Flannel or Calico. So in that sense, it's very interesting. So we can talk about this, or maybe also make a collaboration in the future. We can discuss if you're interested. We can see.
Interesting. Cool. Thank you. Thank you very much.
Thank you as well.
Thank you both. Very, very constructive talk here. Thanks a lot for your contributions, for also sharing or opening possible collaborations. This is very important if we really want to go ahead in this problem. Okay, great. So this is now the time for the webinar closure. Of course, if there are some other questions, we still have 2 minutes to ask. In case you want, please use the microphone or the chat. And if not, well, this is the last moment to firstly thank you really especially to the presenters, for adapting very accurately to the timing. It has been very great. And also for Frederik. Well, Frederik is saying bye-bye and thanking for the session. Thank you, Frederik, for attending. And as I was saying, it has been very, very interesting, very fruitful, I would say. And hopefully in a few days, all these videos and, of course, papers will be available in social media and also in the project's websites. I encourage you to check the websites and download the information you need, okay, regarding the session. So nothing else from my side. Thanks again to the 3 projects participating in this webinar. I think this kind of ideas of sharing knowledge is very important for the progress of in this case drone applications, right? So thanks a lot. Hopefully we will see each other very soon in another webinar, maybe several months ahead. We will send you the information with time enough so that we can guarantee the maximum impact of the session. And well, thanks Garbine, particularly for organizing the session so briefly and easily for the rest to join and to share the presentations. And nothing else from my side. Take care and enjoy the rest of the day. Thank you for coming. Bye-bye.
Thank you very much.
Thank you. Bye-bye.
Bye-bye.
Thank you.
Bye-bye.